So now that we've talked about quadratic functions, we're going to move into talking about polynomial functions. Particularly today, we'll be talking about graphs of polynomial functions. So you definitely looked at this in Algebra 2, so hopefully a lot of this will be review, but there might be a couple of things here and there that might be new for you. So we're going to talk about graphs of polynomial functions, which means we have to first talk about multiplicity, and we have to talk about the degree of a function. So when we talk about multiplicity, we're talking about the number of times that a root occurs in a function. So the multiplicity could be just 1. It only occurs once in a function. It could be 2, it could be 3, it could be a number of just any number of times. But that multiplicity is also going to help inform on the graph of the function. So the number of times that root occurs will tell us what the graph will look like at that root. Now when we talk about the degree of a function, there are two forms that your polynomial function could be in. If it's in factored form, the degree of the function is going to be the sum of the multiplicities of all the roots. On the other hand, if it's in standard form, in other words, if it's all multiplied out, then the degree is whatever the highest exponent is. Okay, so if it's in factored form, the degree of the function is the sum of the multiplicities. In standard form, if it's all multiplied out, then it's the highest exponent. Now, how do we know what the graph looks like at certain roots? Well, these are probably the ways that you have seen this in Algebra 2. When you have what we call a cross behavior, so in other words, at that root, so at that point on the x-axis, if the graph simply crosses there, that means there is a sign change, right? It goes from either being positive to negative or negative to positive. There's some sort of sign change. And this occurs where you have a root with multiplicity of 1. So here's an example of a cross, right? So nothing crazy here. It's just simply crossing the x-axis at that root at that point, and that means that the root has a multiplicity of 1. Now, there can also be a behavior called a bounce, okay? And this is simply what we call a point of tangency. So there's no sign change here. It simply touches the x-axis and then goes back to whichever side it was on before. So if it was below the x-axis, it just touches it and stays below the x-axis. If it's above the x-axis and it just touches it and then it stays positive, goes back to being above the x-axis. Now in the past, you may have learned this as occurring when you have a root with multiplicity of 2. Now that's true, but we're going to extend our definition here, and this actually occurs at a root that has an even multiplicity. So here's an example of a bounce. So you can see at the root that's on the right over there, that I've put a more clear point there for you to see. It is just touching it and then going back down. So it does not cross, there's no sign change. It just touches and then stays negative. Now if you see this, this means that this could be a root with multiplicity of 2. It could be a multiplicity of 4 or 6, as long as it's an even multiplicity. The last behavior that you'll see is what we call, depending on your teacher, you may have learned it as a squiggle, you may have learned it as a wiggle. In either case, what it really is what we call a change in concavity. And that's a term that you'll see more and more, especially as you get into calculus. So this occurs at a root that has an odd multiplicity. So in the past, you may have learned it as when it's a multiplicity of 3. So it's as long as it's a multiplicity that's odd and greater than 1. We know at 1, it simply crosses. But if it's 3 or 5 or 7, then that's when you have this kind of behavior. Now, I think the easiest way to kind of explain how to draw this, I know some people have a hard time trying to figure out how exactly do you draw a squiggle or a wiggle. So think of it as kind of like you were about to draw a bounce. So for a bounce, it usually starts curving and getting really, really close, but curving as you approach that x-intercept, you approach that root. But instead of actually bouncing, you actually cross over to the other side, and then it also kind of looks like the end of a bounce on the other side as well. So you can think of it as sort of between a cross and a bounce. It curves like a bounce, but then it doesn't actually bounce, it actually crosses. Okay, another thing we have to talk about is what we call the end behavior. So the end behavior is the behavior at the extreme ends of the graph. And these, what happens, really what we're talking about is on the far left and on the far right. Those behaviors are determined by the degree of the polynomial and by the leading coefficient. So the degree of the polynomial if it's even or odd, and the leading coefficient if it's positive or negative. So we're going to go through this chart and fill out exactly what you can expect. So if the degree of the polynomial is even, and the leading coefficient is positive, then on the left, it's going to be up, and on the right, it's going to be up. Now, I find it easiest to kind of think of a simple example to help remember the end behavior. So for example, if you have a quadratic, right, that's a degree of 2, that's even, and a leading coefficient that's positive, then you know you have a parabola that faces upwards. So on the left, it goes up, and on the right, it goes up. That's kind of a simple example to help you remember. Now, if the degree of the polynomial is even, but the leading coefficient is negative, so you can think of a simple example as a parabola that's facing down, right? Then on the left, the end behavior is going to be going down, and on the right, that's going to be going down as well. And then lastly, we're going to talk about the two cases when you have an odd degree and the leading coefficient is positive versus negative. So when the degree of the polynomial is odd, the leading coefficient is positive, then on the left, it's going to be going down, and on the right, it's going to be going up. Now a simple example to remember is x cubed here, right? X to the third is a polynomial with odd degree, and the leading coefficient, if you just use y equals x cubed, that would be a positive leading coefficient. So if you think about what y equals x cubed looks like, on the left it's going down, and on the right it's going up. And our last case is if the degree of the polynomial is odd, but the leading coefficient is negative. In this case, it's going to be just the opposite. On the left, it's going to be going up, and on the right, it's going to be going down. All right, we'll do some examples together. So in this first example, you're given a graph, and you're asked to write a possible equation for the graph. Now, I say possible because there are some things that we don't know. So for example, if it bounces, we know it's some even degree, but we might not necessarily know that it's going to be degree 2. Could be degree 4, could be degree 6. Another thing that we don't know is there could be a coefficient out in front of the entire polynomial, which doesn't affect the roots, but it may affect where, for example, the y-intercept is, or how far up it goes before it comes back down. So let's write a possible equation. Let's start by writing out the roots. So notice, where does it cross the x-axis? At -3, -2, and +1. So that means we're going to have a factor that's x plus 3, one that's x plus 2, and one that's x minus 1. Now look at the behaviors at each of those roots. So at -3, it just crosses, so that's degree 1, that's fine. At -2, that also just crosses, so that's degree 1 as well. And then at 1, this, however, is not a bounce, it's not a cross, This does in fact look like a squiggle slash wiggle, whatever you want to call that. And in this case, because you know that it just has to be some odd degree greater than 1, you could say that that's 3. You could say it's degree 5 or 7, as long as an odd degree greater than 1. So we'll just say 3, for example. So that is one possible equation. Another possible equation is you could have, say, like a 2 out in front of everything. That's also possible. That won't change where the roots are, because 2 would not be a factor. You would have to have x in front of it and put it in parentheses to create another factor. But what it does is it does affect where the y-intercept might be. But here, you're not told anything about the y-intercept, so you don't have to worry about that. Okay, example 2. Write a possible equation for the graph below. All right, so same thing. Let's find all those roots. So we have one at -3, at -1, and at 2. So looking here, we have at -3, it looks like we have a cross there. So degree 1 is fine. At x plus 1, here it's not just a simple cross. It definitely crosses, but it looks like it kind of curves like it's about to bounce, but then it's not actually bouncing, so it looks like it's a squiggle or wiggle. So this would have to be degree 3 or 5 or 7 or 9. Okay. And then lastly, we have x minus 2. And that one is a very clear bounce. So again, for a bounce, it could be degree 2, or degree 4, or degree 6, and so on. So here's one possible equation for this graph. Okay, let's do an example where instead of being given the graph, we're being asked to sketch the graph. So we have negative, parentheses x plus 2 cubed, x minus 4 cubed, and x plus 1. Let's start by putting in where all the roots are. So x plus 2 means there is a root at -2. X minus 4 means there's a root at +4. And x plus 1 means there's a root at -1. Okay, so we put those all in. Okay, so the next thing I like to do is take a look at the end behavior. So to figure out the end behavior, remember we're looking at two things: the degree of the function and whether the leading coefficient is positive or negative. Now if you look at the degree of this function, since it is in factored form, you want to add the multiplicities. So in this case, the multiplicities are 3, 3, and 1. If you add those together, we get 7. That is an odd degree. Now, the leading coefficient, if you look out in front, there's a negative there. So we have an odd degree with a negative leading coefficient. That means that the end behavior is going to be up on the left and down on the right. And then we fill in between, and we know at -2, this is going to have some sort of a squiggle. So it'll come down, looks like it's going to bounce, and then actually go through. And then at -1, it just crosses. So it goes back, crosses right back over. And then at 4, we know it's going to squiggle again. So once it comes back towards 4, again, it's going to look like and curve like it's going to bounce, but then actually go through.